Hey everyone, and welcome to The Explainer. Today we're unpacking something absolutely massive in the world of open frontier AI. We're looking at Kimi K3. Now, this is a model that sits right at the absolute cutting edge of capability, but doing so brings up a really fascinating paradox. Basically, how do you scale an artificial intelligence to these unprecedented sizes without needing, an impossible amount of computational power to actually use the thing? Well, today, we're going to break down Kimi K3's architecture and see exactly how it solves that paradox, acting as the ultimate efficiency engine.
Okay, let's dive into this. 2.8 trillion. Yeah, you heard that right. That is the total parameter count of Kimi 3. And on top of that, it boasts a staggering 1 million token context window. I mean, in the landscape of open-weight models, these numbers are highly intimidating. We're looking at a 3 trillion class model that's processing vast amounts of information, text, images, video, all simultaneously. But this sheer scale immediately introduces our core mystery, right? How do you actually run a model this massive efficiently? Traditionally, 3 trillion parameter models require astronomical amounts of compute. They are notoriously expensive to train and honestly even more expensive to deploy for everyday users. If you have a 1 million token context window, the memory and processing demands usually scale quadratically. That makes it incredibly difficult and expensive to serve at scale.
So how did the team behind Kimi K3 actually solve this? Well, we're going to look at their approach across 5 main areas: the 3 trillion parameter challenge, doing more with less, rethinking attention and memory, hardware and deployment optimization, and finally, efficiency in action.
All right, let's kick things off with Section 1, the 3 trillion parameter challenge.
See, jumping to a 3 trillion scale requires a complete rethinking of how a model activates its neural network. You literally cannot just brute force it. The contrast here is actually pretty stark. While Kimi K3 possesses 2.8 trillion total parameters, it only uses 104 billion active parameters per token. And that right there is the first major efficiency hurdle solved. Basically, Kimi K3 doesn't use its whole brain at once. By sparsely activating only the necessary pathways for any given piece of information, it drastically cuts down the processing power required to generate a response, all while keeping that vast knowledge base of a 3 trillion parameter system on standby.
Moving right along to Section 2, doing more with less.
And this brilliantly illustrates exactly how Kimi K3 achieves that massive sparsity. It's all about its advanced mixture of experts, or MOE architecture. If we compare K2 and K3, K3 utilizes a framework called Stable Latent MO. It relies on this vast network of 896 routed experts, but for any given token, it only calls the exactly relevant 16 experts. When you compare that to K2, which had 384 experts and activated 8, K3 is just significantly larger and way more granular. Because of this highly specialized routing, which is stabilized by what the engineers call quantile balancing so no single expert gets overloaded, K3 achieves about a 2.5 times gain in overall scaling efficiency. It basically just converts compute into intelligence much more effectively.
All right, Part 3, rethinking attention and memory.
Because, let's be real, compute is only half the battle. If you want a model to remember a 1 million token conversation, which by the way is like reading several thick books all at once, without crashing the whole system, you have to revolutionize memory efficiency. Enter Kimi Delta Attention, or KDA. Simply put, this is a hybrid linear attention mechanism. Standard attention mechanisms scale quadratically, meaning if you double the context, the compute cost quadruples. KDA completely replaces that standard quadratic attention in a subset of the model's layers. Think of it kind of like a highly efficient filing system. Instead of constantly rereading every single document just to find a connection, KDA compresses and retrieves memories in a linear fashion. That saves massive amounts of compute while maintaining the model's full expressiveness for complex tasks.
And building directly on KDA are these tangible benefits, mostly driven by a companion tech called attention residuals, or ATNRES. Usually, models accumulate memory uniformly, layer by layer, which means they're carrying a really heavy load the whole time. But ATNRES allows the model to selectively access representations from previous layers across the depth of the network. It combines constant-state recurrent memory with selective depth-wise access. And since it eliminates that bulky uniform memory accumulation, it massively speeds up text generation. We're talking up to 6.3 times faster decoding, which is huge.
Which brings us to Section 4, hardware and deployment optimization.
It's one thing to sketch out an efficient architecture on a whiteboard, right? It's entirely another to actually fit it onto commercial hardware for developers to use. The crucial point here is how they handle the physical size of the model, and they do it through MXFP4 quantitation. Why this matters? It means this massive model actually learns to compensate for its smaller, packed size during its training. Instead of training a giant model and then shrinking it down after the fact, which usually totally degrades the quality, Kimi K3 uses quantization-aware training right from the supervised fine-tuning stage onward. It natively packs its expert weights into this highly compressed mathematical format, and that is what allows this 3 trillion parameter giant to run efficiently on standard, commercially available GPUs.
This highly compressed format then feeds directly into a complete developer-ready deployment pipeline, so developers aren't just left to figure this out on their own. The model comes with day zero support for highly optimized inference engines like VLLM and SGLang. By utilizing KDA-aware prefix caching, the system easily manages recurring memory states. And because it's specifically designed to scale across supernode configurations of 64 or more accelerators, the open-source community can start running this incredibly efficiently right out of the gate, distributing the workload perfectly.
And finally, Section 5, Efficiency in Action.
We've talked a lot about the theory, the compute, the memory, and the hardware. But what actually happens when you put all of this together in the real world? Well, now what's really interesting here is this figure, 21%. See, Kimi K3 features this always-on thinking mode. Now, you would naturally assume that a model constantly reasoning and thinking out loud before giving an answer would be wildly inefficient and crazy expensive. But benchmark testing showed that Kimi K3 actually used 21% fewer output tokens than its predecessor, K2.6, to complete the exact same complex evaluations, all while hitting higher intelligence scores. Its efficiency engine makes its reasoning highly economical.
And this translates directly into incredible market viability. According to Artificial Analysis, quote, Kimi K3 costs an average of $0.94 per intelligence index task, which is similar to GPT 5.6 Sol, and approximately half the price of Opus 4.8. The architectural brilliance of KDA and Latent Mo, it's not just some academic exercise. It literally results in a frontier-level model offering highly competitive and accessible API pricing.
And because it is so cost-effective to run, it can basically be left alone to perform sustained, long-horizon tasks. Just look at these real-world achievements. Kimi K3 built a GPU compiler called Mini-Triton completely from scratch. In a 48-hour autonomous run, it designed, optimized, and verified an actual inference chip using open-source tools. It generated a fully procedural 3D open-world game combining coding and visual feedback. And honestly, incredibly, it autonomously executed computational astrophysics research, reviewing papers, implementing pipelines, and generating interactive dashboards in just 2 hours. That is a workflow that would typically take an experienced researcher weeks. It basically leverages its efficiency to sustain massive autonomous engineering and research tasks.
By solving the paradox of scale versus efficiency through sparse activation, linear attention, and native quantization, Kimi K3 has well and truly unlocked frontier intelligence for everyone. We are no longer bottlenecked by the sheer physical size of the models, so I'll leave you with this thought. With 3 trillion parameter models now running efficiently in the open source, what will developers build next?